Good morning everyone and welcome to today's webinar FloEFD for Solid Edge. In today's webinar we will first look at what exactly FloEFD does and then walk through the step-by-step process of setting up and solving a model for a flow analysis, which involves the preparation, the analysis setup, meshing, solving, and then post-processing. At the end we will solve a model for flow analysis, which will also involve heat conduction, and then we will point out the differences. So FloEFD solves a fluid flow and heat transfer problems where fluid flow includes the movement of any fluid caused by external forces, and heat transfer involves energy transfer between two surfaces at different temperatures. So here we have a picture of a man holding a vessel with boiling water. Is a great example of all three modes of heat transfer. So firstly we have conduction, where the heat transfer happens through the handle. Then we have convection, where the heat transfer from the bottom of the surface to the moving fluid, which in this case is a water. And then finally we have radiation, where heat waves are emitted into the atmosphere. So before we start the analysis, the key here is the geometry preparation. So we do the geometry preparation so that our meshing is really optimized. All the results obtained are entirely dependent on the mesh utilized for the model. So four main methods of geometry preparation are suppress, replace, disable, and delete. So suppress is going to remove the data from CAD but not delete it. Replace is going to replace some complex parts with simplified versions to reduce the solve time. Disable will only disable in the CFD environment, but you can still view the data in CAD. And then delete is going to irrecoverably alter your data, which again is not recommended. So what exactly should be suppressed? The features within the parts which you may need in the future or more for a more detailed analysis can be suppressed. So some of the examples of the features that can be suppressed are fillets. Then we have chamfers. We have the threads, holes, internal details, or any features with the complex detail which are not going to impact the results can be suppressed. What exactly can be replaced? So any significant parts of the analysis which are complex at the moment. For example, you can have a simplified version of a fan or a pump or heat pipes or any other sheet metal items. And then what can be disabled? The parts that are irrelevant to the analysis. So in this case, since we are doing a CFD analysis, the parts that can be disabled are nuts and bolts, washers, fasteners, gaskets. So these all parts are not required and can be disabled in the CFD environment. Some other tips for the geometry preparation are that if you're doing an internal type of flow analysis, just make sure that all your ends are closed. So make sure you create the lids. And in case if you forget to create the lids when performing an internal type of analysis, FloEFD has the capability to automatically create a lid, which we will take a look at in the actual demonstration here. Then before you start an analysis, make sure that you perform a check geometry operation. So this is really helpful to make sure that all the necessary internal details are captured, or internal areas are captured where actually the flow analysis will be happening. And then make sure that if you have assemblies for flow analysis, make sure that you don't have any superficial constraints that are not possible in real life. So this is what your analysis setup window is going to look like. So on the right hand side we have two screenshots here. So one is a screenshot where you can take a look at the analysis setup wizard, where you have the option to select the unit system, the project name, the analysis type, whether it's internal or external type of analysis, what kind of fluids do you want to include in the analysis, the wall conditions, if you want to include heat transfer. And then you have other options to create a new analysis, or even clone the project, so that if you want to make a slight change in the existing analysis, so that can be performed using the clone option. So this is what the analysis setup window is going to look like. And next key feature here is the meshing. So FloEFD has a well-defined and robust algorithm to generate a detailed mesh for CFD analysis. So FloEFD supports fluid cells, which, as the term says, which would only be used for fluids, then solid cells, which will only be used for solids, and then we have something called as partial cells. So partial cells are present at the fluid solid interface, so which will include both fluid and the solid at the same time. Solution adaptive meshing in FloEFD is a great tool when it comes to refining mesh and localized volumes based on the type of flow gradients, because it requires little to no user input. You will be able to generate a high quality mesh even if you're not an expert user. So this allows to refine only in critical areas, which in turn reduces the solve time, and it is going to help you to increase the accuracy of the model. So once you have meshed and all the loads are defined, you can start solving the model. So once you start solving the model, this is what your solver window is going to look like. You have two different windows here. It's called as the info window and a log window. So info window will give the information about the total number of fluid cells, solid cells, partial cells, the computational time, the number of iterations performed so far. And the log window will give you information about the refinement table, when the time when the calculation started, and when it is going to be finished. Also in FloEFD, you have the option to preview the plots using the preview settings. So we are going to take a look at that in the demonstration here in a while. And after solving the model, you have post-processing, where this post-processing can be categorized into two different groups. That is going to be your visual results and your numerical results. So visual results are going to be the cut plots, surface plots, isosurfaces, and flow trajectories, that you can take a look at how the fluid is flowing in the flow trajectories. And the numerical plots include the particle studies, the XY plots, and the goal plots that were defined in the analysis setup and report generation. So this is the step-by-step process that you're going to follow when you set up your model for FloEFD analysis and then reviewing the results. So now let's jump into Solid Edge and take a look at how exactly FloEFD works in action. So here I have a ball assembly, as you can see, and I have made the body of this ball valve translucent, so that we can see the flow trajectories, the cut plots, and so on. So once you have a FloEFD installed on your machine, you'll have a flow analysis tab in the command ribbon, and most of the other operations can be controlled here from the edge bar. So as discussed, the first step is where you go and create your new project from the wizard. So here the first option is going to be giving your project a name, adding some comments. So I'm just going to keep this as default. Next step is where you can create or assign units. So Solid Edge has some predefined units. So in this case, I'll be using SI units, but as you can see here, if you scroll down, you also have the option to create new units. So here I've created one new unit named as USA Electronics, and it is specified as user defined. In this case, I'll be using a SI unit, and it is going to be an internal type of analysis. Also make sure that I'm going to make sure that I exclude the cavities that are not going to take part in this flow analysis here. Next step is where I define the fluid. In this case, it is going to be water, so you can simply double click and add it to the fluid tab. This is where you'll be assigning the conditions for heat transfer. So in this case, since we are not doing a heat transfer study, we are going to keep it as the adiabatic wall, and let's use all these default settings here. So once you create and specify all these settings inside the wizard, this is what your computational domain is going to look like. So if you want to go ahead and hide the computational domain, you can do it from your H bar here. You simply right click and hide it, and that easily you can hide this computational domain. So before we start the analysis here, or setting up the analysis for this the specific assembly, we will be doing a check geometry here. So once we perform the check, this gives us the information about that whether the geometry has all the internal specifications, and it also gives you the information about the fluid and solid volume. And if you do a show fluid volume, it gives you a 3D image of how exactly the volume is going to look like. So in this case, you can see this is what the internal fluid volume is going to look like. And as I mentioned in the presentation, since we are doing an internal type of analysis, make sure that your lids are closed. So in this case, I already have created lid parts here. As you can see in the Pathfinder, this is the lid part 1 and lid part 2. If this were not the case, as I mentioned, you can simply create new lids in the software itself. You don't have to create new mates or new parts specially. You can simply go to the tools drop down and say create lids. So this is going to create that lid for you. Okay, so now let's start by assigning the boundary conditions here. So the first step is you simply go and insert the first boundary condition, which in this case is going to be the mass flow rate. So the inlet mass flow rate is applied to the inside face of this lid here. So I'll be using a quick pick command to simply select the specific face I want, and then defining the mass flow rate here. So once you've defined the mass flow rate, it gives you these arrows which indicates that the boundary condition has been applied. Similarly, we'll be closing or creating the second boundary condition here, which is going to be a static pressure. And using the same, and since it's the environmental condition, we'll be using 101325 Pascal. Oh, my bad. Let's select the face here. So I'll be using a quick pick command and selecting the inside face. Okay, there you go. So we have defined the boundary conditions. Next step is where we define the goals. So it is important to specify goals, what exactly you're looking for. So in this case, I'll be using insert a surface goal, and now I don't have to again use a quick pick command here. I can simply select it from the flow analysis tab, which selects that specific face I want, and then use the specific parameter that I want, which in this case is going to be the average static pressure. Next step is where you define the mesh. So here I'm going to create an automatic mesh because it's a very simple model. nothing much complicated here. The only thing that I have to make sure is that the mesh is small enough to cover uh, all the small gaps. So in my case, the smallest gap here is 0.0093 meters, and once you create that, you can take a look at your mesh. So this is how your mesh is created based upon the specifications that you just entered. So now let's go ahead and run the model. So when you run the model, this is what your solver window is going to look like. So before we create all the results here, you can see that I have my my surface plot and my goal plot here that the software is creating here. So from my previous run, since I had already inserted that, it did populate by default. But the other way to populate these goal plots is you go to insert and go to preview. So this is where you'll be defining what plot exactly you're looking for, which in this case is the XZ plot here. As you can see, XZ plot. So you simply have to select that specific axis, I mean the plane. And similarly for the goal plot, all you have to do is simply go to insert again, and just below the preview plot you have a goal plot, and you have to simply check the box and hit OK. So this is the same plot that you can see right here. So I'll start my solver again, and once the results have converged, the solver is going to stop. And here we get a notification that the results have been converged. Now let's take a look at some of the results here. So first, let's take a look at the cut plots. So I'll insert a cut plot here. So for this specific cut plot, I'll be creating a cut plot on the XZ plane. So let me remove the XY plane, and from the pathfinder I can simply select the XZ plane, which is the front plane, and hit the green check box. And as you can see, you can take a look at how exactly your cut plot is going to look like. So there are some other changes that you can do to this cut plot. You can go back to edit definition and add vectors to this cut plot here. So in the display icon, in the display group, you can select vectors. That will add the vectors. Hit the green check box, and if you zoom in, you'll see the vector orientation of how the flow is happening for this specific model. So this is going to be a first cut plot. Second, we can take a look at surface plots here. So again, same thing, it's very easy. You simply have to go and insert the surface plot. In this case, I'll be using all the faces inside that are included in the internal flow analysis here. Hit OK, and it gives you a preview of all the surfaces that were included in the analysis here. Next, we will take a look at the flow trajectories here. So when you're trying to define flow trajectories, all you have to do is simply define the start phase here. In this case, it is going to be the static pressure 2, and hit OK. What you can do is here you can right click and hit play. That will show you how exactly the flow is going to take place inside that specific path. So these are some of the ways that you can interpret the results and view results inside FloEFD. So here I have an enclosure assembly, and will be conducting flow analysis here along with the heat conduction in solids. So let's take a look at that. So initial setup is going to be very similar to what we did for the ball valve assembly. First step is you would go to the wizard, from where you can select the specific units that you want. In this case, since we are doing heat conduction as well, so we'll check the box for conduction. Since this is going to be an internal type of analysis, we'll select internal in this drop down here, and the fluid here is going to be air. And since we are doing heat conduction in solids as well, so we need to specify the specific solid materials here. So in this case it is stainless steel 321. And now we'll start defining the outer wall thermal conditions. In here it is we'll be defining the heat transfer coefficient, which is 5 watt per meter square per Kelvin, and then the temperature for external fluid is 50 degree Fahrenheit. So this is the initial setup that will be taking place when you're doing an FloEFD analysis or flow analysis along with heat conductions. So the first step is, in this case, we have as we'll select an inlet fan on the specific face right here. So we go to conditions and select and fan. So the first step when you select a fan is you specify what phase is the airflow coming from. So in this case I have an external inlet fan, and it's going to be this plain cutout one exactly right here. And then FloEFD has some predefined fans here. So I have an axial fan, so you can specifically decide what exact specifications for that fan you want here. Decide the thermodynamic parameters, the temperatures, and so on, and hit the green check marks once you're done. Next step is where we decide the boundary conditions. So here we'll insert boundary conditions, and we have 3 exit valves here. So we'll select the faces for those 3 exit valves, and like we did in the previous flow analysis model, we'll select all of those faces one by one. It's going to be environment pressure, and here I'll be keeping all the defaults as it is. So once we have decided the airflow and environmental conditions, or you can say boundary conditions here, the next step is where we decide the heat sources. So here we have a couple of heat sources, since this is an electronic assembly. So you go to the sources drop down and select volume source. So the first one here is going to be the main chip part here. So I can select that from the pathfinder directly. Specify the parameters here. So it's 5 watt. You can change the name right from here if you want. So I'll just give this I'll just name this as main chip. So this is going to be my first heat source. The second heat source is going to be these three capacitors here. So I can select them from the pathfinder itself, and we can specify the temperature. So the temperature here is 100 degree Fahrenheit, and name them as capacitors. So these were the 2 heat sources. Apart from that, we have a few more here. So The next step is we have these small chips here, which do have some heat generation capabilities as well. So we can specify that under sources as well. So let's select volume goals. My bad. We go to the drop down, select volume goals. Volume sources. Specify the chip parts from the pathfinder. Decide the heat. It's 4 watt. And finally we have this power supply that is going to be our last source of heat generation in this assembly. So let's give it a name as power supply. And the temperature for which is going to be 120 Fahrenheit. So if you miss to change the name from the edit definition box, you can simply right click here and go to properties and change the name from this feature properties. In this case I would like to rename them as small chips and save it. So that change is applied in the flow analysis tab right here. So since we are doing heat conduction as well, we will have to specify the solids here. So by going with the engineering database and selecting the specific type of material here, in this case I'll go to solids in user define. So I already have defined some materials that I want. So it's very easy and straightforward, where you specifically go to the option and you can change the material properties. Here I have changed the thermal conductivity, the electrical conductivity, and the temperature for some materials, and save that, which I can use now. So here what I'll do is I'll start by specifying the solid materials. So the process to define the solid materials here is you simply right click solid materials on the pathfinder, the flow analysis tab, and say insert solid materials. And now you can specifically decide what specific materials you want. So in this case I want to apply materials from my motherboard and the PCB part 1 and PCB part 1 for both the parts here. And I'll be using the specific materials which are defined, so which I've named as tutorial PCB, and hit the green checkbox. So that's the first solid material. So I have a couple of more solid materials to assign. So for my main chip parts also I have some material here. Go back to solid materials, say insert solid material. So for the main chip and small chips here, okay, so now I selected all the small chips and the main chip, and now I can specifically assign the material which I've named under user defined as a tutorial component package. So specified materials for main chip and small chips here. Next step is define material for heatsink. So as you can see here, we have a heatsink, so we can specify material for this one, which is made up of aluminum. So I'll go back to solid materials here, insert solid materials, select the heatsink, and under predefined materials here, under alloys, oh sorry, it's under metals, you have your aluminum material, so that gets added as well. And lastly we have the material for inlet lid and outlet lid parts here. So go back to solid materials and select this inlet lid and outlet lid. So inlet, which is the fan lid, and this is the exit, so I can specify all of them here one by one, and all of these are insulators. So under predefined, if you go to glasses and minerals, you should have the option for insulators here. So now that we have assigned all the materials, boundary conditions, inlet fans, heat sources, the next step is where you decide you define your goals. So in this case, I have two volume goals, two surface goals, and one global goal to define. So you can define goals from the flow analysis tab. You say you want to insert a volume goal. So here, what exactly do I want? So first step is I want to I want to check for the maximum temperatures for my small chips and main chip. So I'll say main chip and say, if you scroll down, you have the option which says solid temperature, and check the box for max. Next volume goal is to check the temperatures for small chips. So I'll say small chips, and again scroll down, check the box for max temperature. So now we have two surface goals here for the inlet and exit. So specify that surface goal on the inlet face, and what exactly we're checking for is the average static pressure. So the first one where it says static pressure, you can check the box for average, which will check for the average static pressure. And then finally we can check the mass flow rate for the exit here. So go back to surface goals and the surface goals, and check for mass flow rate for the environmental pressure right here. And lastly, we have to define the global goals here. So globally, we are going to check for the average static pressure and average fluid temperature. So now that we have defined all the goals as well, let's go and change the let's go and change the mesh size. So here I know that the minimum distance between the smallest gap here is 0.1 inches. So I have defined that, and you can see that my mesh has been created here. If you want, you can hide the basic mesh and run your solver. So just finished solving the model here, and now we can go ahead and check for the results. We can simply go and check for the flow trajectories like we did for the ball valve assembly. Specify the phase from where you want to check. So in this case, it's going to be the inlet phase right here. You can specify the number of arrows, bands, the size, or I mean the width. If you check the box, it will run a status check, making sure everything is right, and this is what your flow trajectory for this specific assembly is going to look like. You can hit play to check how exactly this whole trajectory or the flow is going to look like from start to the end. Next, we can check for some cut plots here. So let me go ahead and hide this first result. And next, we can go and check for the cut plot. So say insert cut plot, and let's use the XY plane here as a plane to check the cut plot. So here first let's check for the velocity of the flow. You can simply do that by changing the parameters here. So under contours, you can simply say you want to look for the velocity, making sure it's still XY plane, and this is where you can add the offset distance. with respect to the specific plane that you have selected. So this is the velocity distribution. As you can see, it's going to be red at the inlet because this is where the flow is starting from. So you'll have high velocity around 4 meters per second at the inlet, and then it is distributed as you can see here. So since we are doing a heat conduction analysis as well, so under the cut plots we can also check for the temperatures. So go back to edit definition, and now instead of velocity, let's go ahead and check for the fluid temperature here. So from the drop down, let's say you're checking for fluid temperatures. From here you can specify the number of levels. You can add vectors if you want. You can specify the min and max. So let's say if you want to check the fluid temperature distribution between 120 degree Fahrenheit and 50 degree Fahrenheit. So you can do that. Also you can specify the min and max for velocity as well. So we can do from 0 to let's say 10 feet per second. So if you take a look at the top view, this is what your fluid temperature distribution is going to look like. Also, we can take a look at some of the surface plots here. So let me go and hide this cut plot, and now let's take a look at the surface plot, and the parameter that we'll be checking is the solid temperature. So let's go and add, so say insert for the surface plot, and what we'll be adding here is all the chips. So the main chip, the small chip, and the heat sink. So you can add main chip, small chips, as well as let's select heat sink from here, and from the drop down we'll say solid temperature. Hit the green checkbox, and that should give us a distribution. If you take a closer look here, you can see the temperature distribution and all the colors based on the contours here, how exactly the solid temperature distribution looks like. So this is how in FloEFD we can, along with flow analysis, we can also check for heat conduction. So thank you for attending the webinar today, and I'm open to any questions that you might have.